Welcome back to 288X. I'm Professor John Hart from MIT, and today we'll focus on additive manufacturing, which you may also know as 3D printing. Now, even if you've never used a 3D printer or designed a part for additive manufacturing, you know that this represents a very important technology to manufacturing now and more so in the future. And we can see many examples of this importance based on what industry is doing with additive manufacturing. For example, GE starting to print parts out of metal for their jet engines, Google thinking about deploying modular products such as smartphones where the cases are made using 3D printing, doctors printing custom parts to save people's lives using 3D printing, and consumer products companies such as Nike thinking about making custom personalized shoe soles. We'll get back to these examples later on, but you may have also heard that 3D printing was invented at MIT, and that, in terms of one particular process that's still used today, is in fact true. This is a photo of one of the first parts made on MIT's 3D printer, made about 25 years ago. At that time, Professors Ali Sachs and Michael Sema and colleagues invented the 3D printing technology, which involved building parts up layer by layer from a powder-based material, where the powder was glued together using an inkjet printing technology. Now, this is a small model of the Hagia Sophia, a famous landmark in Istanbul, Turkey, and you can see the fine level of detail they achieved, and also that the part has hollow internal cavities. That's one of the hallmarks of the flexibility of 3D printing, and that was seen and demonstrated in this part. In fact, I have one of the several remaining parts that floats around various offices at MIT here in my hand, and we can see it under the camera. And by looking at the top surface of a part, you get the sense of the fine degree of texture as well as the granularity. That's both a strength and a weakness of 3D printing overall. And if I turn it at an angle, you see the tall, thin features that could be created, as well as the layers from the side, the staircasing of the side of the part, and the internal cavities that I mentioned before. So this immense flexibility in geometry, as well as the limitation in the resolution and level of detail, is an important attribute when comparing and contrasting what additive manufacturing can do compared to conventional manufacturing. As you might expect, the inventors of 3D printing at MIT received a patent. Their patent was granted in 1995 and filed several years earlier, and their patent is in fact entitled Three-Dimensional Printing Techniques. Here's a basic schematic of the process where powder is spread inside a build tray, which we sometimes call a powder bed, and after each layer of powder is spread, an inkjet deposition system deposits a liquid that binds the powder together in the areas where the part is to be formed, thereby taking each consecutive layer of the part and binding together those areas that you want to remain and built into the 3D geometry. You perform 3D printing. And they received quite general claims for their technology, and this 3D printing technology led to several successful entrepreneurial efforts. If you come to Cambridge and you visit the MIT Museum, you have the chance to see this printer. This is one of the original 3D printers on which parts like we showed were made. And in some ways it's similar to 3D printers today. It contains the printing mechanism. Here's the powder bed in the inkjet printer. It contains a computer for controlling the process. Then it contains a lot of electronics for communicating the instructions to the printer itself. But of course, the component technologies have advanced a lot since then. And while we're very proud at MIT that 3D printing was invented here, and it was important to the early growth of this industry, there are a lot of other examples of early additive manufacturing or 3D printing. For example, about 10 years earlier than that part at MIT was made, a fellow in Japan named Kodama invented the first 3D photopolymerization process, analogous to what we today call stereolithography. He took a photocurable polymer, one that can harden when exposed to light, and layer-wise stacked up layers with different cross-sections and made parts such as this small house model made by his process. Now, it's quite poor in its level of detail and accuracy, but it demonstrated the basic concept. Another popular printing technology, particularly for metals, is what's called selective laser sintering or selective laser melting. And that has advanced rapidly only in the recent few years. But as early as 1979, researchers were thinking about this. In fact, not a researcher, but a gentleman in Las Vegas, Nevada in the US, named Ross Householder, got the first patent on what looks similar to laser sintering today. The story is he would drive to work through the desert outside of Las Vegas every day, and he would look out the window of his car and he saw the sun shining down on the sand of the desert. And he had the idea that he could build parts in 3D by this process. So he filed a patent, he was granted that patent, and then demonstrated the process not using a laser but just by forming consecutive layers of sand. And then he moved on to other things in his career, but his patent was licensed by researchers who started the first metal 3D printing company about 10 years later. And that company was founded by faculty at the University of Texas at Austin. So like in many industries, we see early innovations, and then we recognize the time it takes for the technology to really come to fruition and have mass market impact. And that's why we're so excited about additive manufacturing today. And all of these processes taken together subscribe to one key difference. In previous lectures, particularly on machining, we talked about material removal, what we might call a top-down process. Here in CNC machining, we of course start with a bulk workpiece and we remove the material needed to create our final part. That contrasts additive manufacturing, which is intrinsically a bottom-up process. We're able to build up materials into free-form geometries into the parts that we want one layer at a time. And by adding material from the bottom up, layer by layer, as seen in this simple desktop 3D printer, which uses polymer extrusion, we can build a great variety of geometries, and we generally don't have to have tooling like we do in processes such as injection molding. So appreciating these differences, the advantages and disadvantages, and where they stand today and in the future is important to project the impact of additive manufacturing. Now, we probably have a definition of additive manufacturing in our minds already, but to go to the textbook or the standards book, we can say that additive manufacturing refers to a process by which digital 3D design data is used to build up a component in layers by depositing material. That applies to all the processes we've already discussed, and this definition comes from the ASTM Standards Committee on Additive Manufacturing Technologies. This committee has been formed over the past few years to come up with terminology and standards that help grow the industry and let different stakeholders talk to each other on the same terms. And it's okay to call additive manufacturing 3D printing. In fact, it's one of the original processes and that very cool, catchy term that we all use. However, we're starting to say additive manufacturing because we're thinking of the techniques not only for printing or prototyping rapidly, but for possibly making large quantities of parts in the future. And therefore, we say that additive manufacturing is more accurately described as a professional production technique which is clearly distinguished from conventional methods of material removal. So here we are in 2016, thinking about what additive manufacturing can do for us in our careers today and what it will do in the future. So why is it such a big deal now? It's been around for 30 years or more, or at least those key processes were invented so long ago. Well, I think there are many reasons, including those listed here. First, we now have wide access to CAD/CAM software, computer-aided design tools that let us create geometries for 3D printing. We have improved automation and component technologies of 3D printers significantly over the past several years, and their cost has gone down. I'm talking about low-cost motors and mechanical components, as well as things like lasers that drive laser metal printers, for example. We also have a growing library of printable materials, the feedstocks, the filaments, the powders, the photopolymers that go into 3D printers. And in the additive manufacturing industry, we're starting to see many materials companies get into the game because they now see significant business potential. We also have major industry and government investment. Those folks want to encourage the growth of the industry because they see its big applications. And we also see that there's more freedom to operate enabled by patent expirations. Now, many of the original 3D printing companies still survive with great momentum, but a lot of those cornerstone patents have expired, which lets new folks enter and innovate in new ways. And all of these things together, in my opinion, lead to significant momentum and confidence and creative vision. And at the end of the day, I think additive manufacturing is a truly amazing technology. It may be many, many years, if not ever, before we make a majority of what we do by 3D printing, by additive manufacturing, but we don't yet even know the possibilities that it can create. So as we go through this module, here's the chapters we're going to present. First, I'll talk in more detail of what you can actually make using additive manufacturing and why it's so important. Then we'll present an overview of the major additive manufacturing processes, of which there are more than we can address. And we'll talk in detail about three mainstream processes: extrusion additive manufacturing, which you might know as fused deposition modeling, or FDM, photopolymerization, called stereolithography, and powder bed fusion, most commonly referred to as selective laser sintering or selective laser melting. Then I'll briefly talk about just a few of the most exciting emerging additive manufacturing technologies and ways of combining things like electronics with 3D printed parts, and then we'll conclude. Hello again. So I just told you that now is the time for additive manufacturing. But why is additive manufacturing so important, and what can it do for industry? Well, first let's look at the size of the additive manufacturing industry today. The Wohler's report, which is published every year, surveys manufacturers and users of 3D printers and counts the total annual value in billions of dollars of sales of additive manufacturing machines, 3D printers, and additive manufacturing services, in other words, 3D printed parts that are sold. And as of last year, 2015, they say it's about $5 billion a year. This has been growing at an annual rate of about 25% per year for the past 27 years. The report's been collecting data for 27 years. And while the 2015 growth was 26% right on average, you can see from this chart that the rate of increase is growing. So we're in a rate of rapid growth of the additive manufacturing industry. Now, $5 billion is a lot. But relative to worldwide manufacturing, which is, however you look at it, over $10 trillion per year worldwide, a significant fraction of the world economy, if you divide the two numbers, additive manufacturing is far less than 0.1%. So in one sense, we might say it's early for additive manufacturing. In another sense, the impact on the bottom line of manufacturing is small. But when I think $5 billion, a big amount of money, but not a big amount of money when you look at the revenues of major corporations, and compare that to the diverse industrial uses of additive manufacturing, I think there's a bit of a discrepancy. And this discrepancy is comparing that $5 billion in measured value with the amount of investment in the technology and the derivative benefit of the technology, benefits implied by applications such as this. For example, General Electric has announced significant investment, over $1 billion in metal 3D printing for jet engine components and other components of aircraft, with one specific advantage being that their future 3D printed jet engine fuel nozzle can improve the efficiency of their jet engines by increasing the combustion temperature in the hot zone. Other aircraft companies such as Airbus are printing brackets for use in aircraft. This is a simple cargo door bracket, but the flexibility of 3D printing lets them achieve the same function at lighter weight, and that of course saves fuel in an aircraft. Here we see an example of use of 3D printing in Hollywood special effects. Believe it or not, Hollywood was one of the first users of the original MIT 3D printing process. Here, from the movie Skyfall, the recent James Bond movie, they made, by 3D printing and assembly and post-finishing and painting, replicas of the Aston Martin DB7, and this was more cost-effective than, unfortunately, destroying real cars for special effects. A more personal application in medical devices. This was recently published in the New England Journal of Medicine. It's a case where doctors and engineers at the University of Michigan Hospital got together and 3D printed an implant for an infant with a collapsed airway. This was 3D printed using a biocompatible material, and it was strapped around the infant's airway. This is a very, very small part because it's a very, very small boy, and they followed the boy's health for years afterwards. It's now been a couple of years, and it published that they believe it saved his life and will biodegrade within the next couple of years. There are also great applications in tooling, where here you're not making parts, but you're using 3D printing to improve the performance of tooling. For example, enabling conformal cooling channels close to the surface of an injection mold, and that can improve part quality by making shrinkage more uniform and also reduce cycle time. Nike and many other shoe companies have explored 3D printing of custom shoes. In this case, an example they publicized for the Super Bowl, the American Football Championship a couple years ago. And Google, for example, is thinking of producing a modular smartphone on their Android platform, and they've discussed the use of 3D printing for printing small quantities of custom case components. And it's interesting to think, when we realize the difference in cost versus volume and entry point accessibility for 3D printing, what low volume and modular products we might see in the future. So if you add all of these applications and potential applications up, I think you might agree that the value is greater than expressed in that simple industry number, and the interest is certainly overwhelming compared to that. The Wohlers report also asks, how do you use the parts made on your industrial additive manufacturing machines? And you can see from this chart that the responses are varied. The largest piece of the pie is functional parts, small volume parts used in real engineering applications such as specialty machinery or instrumentation. But there's also 10% in education and research, about 20% in aggregate in various components of tooling and casting patterns, as well as use as simple visual aids, presentation models, and for fit and assembly testing. So this together represents about $2.5 billion a year, and within that there's certainly millions upon millions of unique parts that leverage one of the capabilities of additive manufacturing, making something complex at a low production volume and making it quickly. But there's also a couple applications in the medical industry that already consume large production volumes. The first is what's known commercially as Invisalign. The company Align Technologies for several years has enabled a additively manufactured alternative to traditional metal braces. Now the additive manufacturing actually comes in 3D printing a custom replica of each patient's teeth, and then they have an automated thermoforming process that forms a biocompatible plastic onto custom aligners that are shipped to their patients. The last data I saw said that they produce about 20 million unique parts every year. And their market value, the value of their stock on the US stock market, is about $5 billion. And that's interestingly comparable to the whole industry if you just count the parts and machines. Another great example is metal 3D printed implants. In this case, Arcam and other companies are 3D printing hip implant cups, just one component of the hip implant. This is what's called the acetabular cup, which is the part of the hip implant that gets put into the pelvic bone. And the advantage of 3D printing here is that the surface can be textured in a lattice structure that enables improvement to the rate of integration with the bone. So there's an improvement to the bottom line of the treatment process that justifies the investment in 3D printing. So for these and other applications, why do we use additive manufacturing? An incomplete list I came up with says first, fast prototyping. The earliest application of 3D printing was rapid prototyping, and that's what it was called. Of course, we realize that 3D printing can also make complex geometries, internal cavities, and contorted features that we can't even imagine to create using machining or injection molding, unless, for example, we need to assemble many parts together with a lot of labor and a lot of design time. We're also thinking of 3D printing multiple materials. Multiple materials in one part, traditionally very hard to combine. And the fact that 3D printing lets us deposit materials locally also lets us create new materials by mixing. We can achieve enhanced performance, where that might be the same structural strength at lighter weight or an enhanced performance factor in that regard. And we can also think about doing low-volume manufacturing. What I mean here is not having to invest in traditional tooling for injection molding. If you can 3D print plastic parts, for example, you can create a smaller volume product. And in the case of Invisalign, we have a great example of truly personalized manufacturing, because the incremental cost to personalize the part is small once you've mastered all other aspects of the process. And you might have additional reasons in your mind or in your experience. So back to the first one, fast prototyping. One of my favorite memorable examples is this one from PepsiCo, which has a division that makes food products including potato chips. And yeah, what you see here is a desktop 3D printer literally printing potato chip models. Not edible potato chips, but this conversation is describing their use of desktop 3D printing to create prototype potato chip geometries that can be handed to customers, where they can ask the customers, do you like the look and feel of the potato chip, and do you think you would enjoy eating a potato chip with this texture? So texture is not everything, but it's important to their customers, and here they can reduce the time taken to develop new products and also reduce the risk, so they can invest in the right tooling the first time by using 3D printing in their product development cycle. Now, more from an engineering point of view, we often think about what geometric advantages 3D printing has. So let's think about this coffee cup and imagine what it would take to machine this coffee cup or to machine injection mold tooling for making a geometry like this. Now, if we look closely at the geometry, you can say, well, this has a few distinguishing features. First, it has cavities from multiple directions, the cavity inside the handle and the cavity of the cup itself. These are deep and curved surfaces and complex geometries, and those are generally challenging to machine. And if we put all these reasons together, we can say this is why it's advantageous to think about 3D printing an object like this. For example, in a machining process, the cavity in the middle may be too deep to machine. We would need to have a multiple orientation milling process, like a 5-axis milling process, or multiple fixturing setups if we wanted to achieve the inside and the outside surfaces to get that undercut. And also the complex internal features of the handle and the fact that it is an overhanging curved handle would also be difficult to achieve. So while 3D printing of things like coffee cups would not necessarily be a cost-effective large volume process, we need to open our minds to the flexibility that's possible. And that flexibility is exemplified by the parts I have here. This is the hip implant cup I showed you before. This is actually what it looks like when it comes off of the 3D printer. It has a lot of residual metal powder, and we'll learn about the post-processing steps later on. And then here I have the same part after it's been cleaned up and ready for use, also cut in half to show its texture. And the geometric complexity and flexibility is the surface features right here. This is a complex lattice work that goes against the bone when it's implanted in the patient and improves the rate at which the hip implant adheres to the bone. And good adhesion between the implant and the bone is needed for the patient to recover from the surgery. So this is a direct advantage why 3D printing is used increasingly for these kinds of applications. I also here have some brand new parts from Carbon, which is a startup company based in California. They have a high-speed plastic 3D printing process they call CLIP, which stands for Continuous Liquid Interface Polymerization, and they can print plastic parts with incredibly fine detail. This is a small model of the T-Rex from the Jurassic Park movies, and you can see the really smooth surfaces and complex features of the teeth and of the skin. So this could be used, for example, in a special effects scene if it's painted. And they're also exploring printing the kinds of geometries you can't easily achieve using things like machining and injection molding. This is a flexible elastomeric material that they can 3D print, and you can see the lattice work of the part is quite intricate and also enables it to bend and twist and also recover from the deformation. So you might imagine something like this being inside a running shoe, and that's one of the applications they say they're looking at. So these are just two examples of many materials, many processes, of which we'll build our understanding as we go forward. And now let me ask you, if you've done 3D printing or read about it, what processes have you used? And what was your experience? What do you think about the status of the technology today? So I'll ask, how good or bad is additive manufacturing now in terms of our four familiar attributes: rate, quality, cost, and flexibility? And the answer is, of course, in terms of these attributes of comparison to things like machining and injection molding, the performance is at present quite low. There are a lot of inferior aspects that trade off against the advantages that we discussed. Every process is different and will have a more exact answer. But to be general across the spectrum of technologies, the rate of additive manufacturing is low. The rate, as I measure it, is anywhere from 1/100th to 1 kilogram per hour. This is getting better quite quickly, but think of machining or injection molding at their highest rates being tens of kilograms per hour. In terms of quality, if we look at surface roughness or feature resolution, the finest detail is a measure of quality. Most 3D printing processes are at about 100 microns, or 1/10 of a millimeter. And there's a big trade-off between rate and quality, which is often determined by the fineness at which you deposit material in 3D printing. Cost is also high. Cost is high because of the materials being expensive, the feedstock for the machines, as well as the rate of the process being slow and the machines being expensive. So depending on the material and process, you might pay 10 cents to $10 per gram of 3D printed part. Even a plastic part might cost 10 cents per gram, and when we were discussing injection molding, we were talking about dollars per kilogram. So there's an order of magnitude difference there at least. However, we have truly amazing flexibility for the reasons we just described, and that's what presently trades off against the limitations of additive manufacturing. So it's all about understanding these limitations and deploying it for the applications in which it can create one or more of those benefits. And from this, I think we can see an important contrast in the value proposition for additive manufacturing versus traditional manufacturing. My personal definition of manufacturing is value at scale. If we look around our world, we notice that pretty much everything from food to automobiles to medical devices spends some time in a factory. And traditionally, we must produce a large number or a large scale of products in order to create value for the consumer. If we will look at the cost per unit volume, we have to achieve that economy of scale where we reduce the unit cost of production in order to have a viable business. But I think additive manufacturing is starting to let us redefine value at scale, or achieve value at a different definition of scale. And one reason that's the case is we can think of investing in a 3D printer or a set of 3D printers and a set of materials with a broad set of capabilities. And if we understand enough about the 3D printing process, we can produce different parts on demand in tunable quantities, 1 or 10 or 100, without having to make that fixed investment in something like injection mold tooling. So if we master the additive manufacturing process within our organizations and within our education, we can achieve a flat cost volume curve. And if we think about making parts that are complex or customized and or producing at smaller volumes, we can have a cost advantage against traditional manufacturing. And that's what's shown in this schematic chart, a graph saying ideally the cost per part for additive manufacturing is level, and as we increase the complexity or customization of our product, we can achieve an advantage where we get complexity or customization for the same cost as it would take to produce a simple part. And the cost of traditional methods arguably becomes significantly greater as we have to customize tooling in small volumes, or we have to learn how to create complex geometries that challenge the process. So there's certainly a space of discovery where things are easier and more open if we adopt additive manufacturing. And looking to the future, the same paper from which I cited the bottom chart has this great matrix of 3 axes, saying there are ideally 3 axes of manufacturing flexibility. There's complexity in the parts that we produce, there's customization in terms of their geometry or their function, and then there's volume in terms of the quantity of production. And in traditional mass manufacturing, we're restricted in the complexity we can achieve. We must produce at high volumes, and as a result of low complexity and large volume mass manufacturing, we're restricted in our ability to customize. And now we can think of potentially spanning all points within this cubic space, and in the future potentially achieving arguably complete manufacturing freedom, where we can think of producing individually customized products in small quantities on demand, and we can use the flexibility of additive manufacturing to realize these dreams. To sum up, I really do think we're on the verge of a 3D printing revolution. Or perhaps not a revolution, but a renaissance, where the capabilities of 3D printing and additive manufacturing will allow us to rethink how we design and manufacture our products and how we define business models for manufacturing at scale. Now, this article was recently published in the Harvard Business Review, and it says that 3D printing is going to transform the operations and strategy of a variety of companies, and many companies are starting to think of that for good reason. One salient point that it makes to me is that 3D printing is equivalent to where the internet was in 1995. Now, coincidentally, 1995 was the first time that I walked up to a computer, saw a browser, and logged on and discovered the internet. So I don't necessarily think that 3D printing will scale at the same way as the internet has scaled, but if we make a comparison between where the internet was 20 years ago and where it is now, we can see that there's a lot of room to grow and a lot of exciting things ahead. Welcome back. In this chapter, we'll overview the spectrum of additive manufacturing processes in preparation for a deep dive into the most common and significant ones. The first process that you may know already is called fused filament fabrication, or fused deposition modeling, denoted FFF or FDM. This is what's used in the majority of desktop 3D printers and also is the industrially most common process. It involves extrusion of thermoplastic, typically in form of a filament, in a layer-by-layer fashion, so parts are built from the bottom up. In a crude way, it's like a glue gun that's motorized so it moves in 3D. Now, this is used in most desktop printers because it's the most accessible process with low-cost feedstocks and simple operating conditions, but it's also used industrially, and FDM can be adapted to a wide variety of thermoplastics, similar to those used in injection molding, and can be used in commercial applications such as making ducts for rockets and aircraft. In fact, every Boeing or Airbus plane has hundreds of parts made by FDM. The next process, also typically for polymers, is called stereolithography. It's one of the original ones, invented by Chuck Hull in 1985 or so, but more recently it's taken flight. One example of its recent growth is Formlabs, a company local to MIT that's brought out a desktop stereolithography printer that can create high-resolution parts for applications such as miniature statues, engineering parts, and medical devices. Stereolithography works by scanning a laser across a bath of liquid material. The liquid material is what's called a photoresin, and when it interacts with the laser, it cures to form each point in each layer of the part. This is a much bigger stereolithography machine from Materialise, a company in Belgium, and it's producing components for a prototype automotive dashboard. You see the parts emerging from the liquid bath here, and in a second we'll see the support material that's needed to hold the parts up as they are printed. The third most common process is called selective laser sintering or selective laser melting. It's similar to stereolithography in that it uses a scanning laser, but the laser is much higher power and the laser is melting plastic or metal powder. And that local melting is what creates each layer of our part. Here's a video that I took in a lab in Singapore of a single layer operation of an SLM machine. The bright spot you see moving is the very rapid scanning of the laser, and there's complicated and atmosphere control of the powder spreading, as well as control of the laser and optics, which makes metal 3D printing by SLM still a very expensive process. But the advantages of it are exemplified by the part at the right. This is a test part printed and shown at a recent 3D printing exposition, which is the brake pedal for a Formula One race car, with the idea that it's sufficiently strong but lightweight so the performance of the car can be improved. And we'll learn a lot more details about SLM in a later chapter. Here under the camera I have three parts, three cubes made by the three processes we just discussed. These are like little six-sided die with different features with quantity 1 through 6 on each side, as well as the logo of MIT. And the middle one is made by FDM, made by Extrusion. The left one is made by stereolithography or photopolymerization. And the right one is made by selective laser melting and is made out of stainless steel. If we look more closely at the FDM part, we can see clear evidence of the extruded layers. This is a side view of the part, so it was built vertically from the bottom up, and the stripes you see represent the consecutive layers. That's an important attribute of the FDM process that governs its accuracy and quality. If I flip to the top, you see a secondary material, the white material inside here, and this is residual support material that wasn't effectively removed at the end of the process. And we could have cleaned this up better, but it shows that another support material was needed to keep this overhanging feature stable during the printing process. Looking at the top surface here, you see evidence of the trajectory of the printhead and the discretization that occurs as it fills the top cross-section. If I compare the FDM part to the stereolithography part, you see that stereolithography achieves a higher degree of detail. For reasons we'll learn later, you can scan the laser with higher accuracy and achieve sharper, cleaner surfaces. But one of the limitations of stereolithography is it's intrinsically a single material process, so you're not able to have this secondary support material. So in some cases you need support structures that have to be mechanically removed and therefore the surface finished, which leads to higher cost in post-processing. And here's the metal part for comparison. Let me push these a bit out of the way. And this metal part has in fact been post-processed and polished after being printed. Its surface is still quite rough. The fact that it's metallic makes it shiny. The part's much heavier, cost about 10 times as much as the plastic parts because of the intrinsic printing attributes. And here are some important defects due to the heat flow in the metal 3D printing process that we'll learn about later. So we'll use parts like this to structure our discussion, and like traditional manufacturing, doing the forensics of 3D printed parts lets us understand the process physics, understand the limitations and some of the problems that need to be solved. And considering the complexity of 3D printing different geometries, we essentially need to figure out the process conditions a little bit differently for each part we make. Next we have material and binder jetting, a general class of processes that uses inkjet technology to deposit droplets of material locally. Now inkjet is attractive because it's a widely used printing technology and it can be parallelized, deposit many droplets in a very short amount of time. In material jetting, the part is built by inkjet itself, and this is mainly used for polymers today. And in binder jetting, you deposit a binder to fuse powder together, either plastic or metal or ceramic, and that's an outlet of the original MIT 3D printing process. One of the main companies doing material jetting is Objet, which is now owned by Stratasys, and they have a process that can do multiple polymer materials with different mechanical properties and different colors. That's a unique capability in the industry at present. VoxelJet is one of the binder jetting companies, and one of their big businesses is in making large parts by binder jetting for applications such as sand casting of complex geometries. Last two more processes, smaller in market but still important and unique, are laminated object manufacturing and directed energy deposition. In laminated object manufacturing, you are laminating sheets of feedstock together. You apply one sheet at a time and then cut the cross-section of the layer to form the 3D part. In directed energy deposition, you use a laser to fuse typically a metal together, and you feed the material locally where you want it to be built. And that feedstock can be a powder, as in Optomex process, or a wire, as in Siaki's process. Siaki is based outside of Chicago, Illinois, and they use a titanium wire feed with an electron beam to melt the titanium locally, and they're doing very well in printing large parts for aerospace applications. Back to LOM, I have a couple example parts here. First, this little head model of Lord Voldemort, and this is made out of paper, believe it or not, by a company called MCOR. They're based in Ireland, and their process laminates paper layer by layer to create 3D parts. Now, paper is not the best for certain engineering applications, but it's an attractive material for quick prototyping in the office, for example, and the material is relatively low cost and entirely recyclable. So the part's a little bit dirty, but if you're feeling it like I am, you find it has a fairly smooth surface texture, and their process can also add color to the part, just like you add color to a paper print by inkjet. Here's a metal part made by LOM. Fabrasonic is a company doing LOM of metals, and this test part has different colors visible from the top because we're machined down to the a second material that's beneath the first material. And if I hold this up and shake it, you might hear a little jingle, and that's because they've encapsulated a component inside. This part during the process looks like this. They've added extra material to show how the individual strips are fused together. Here they're fused together ultrasonically, and the advantage of this process is it can join multiple metals. As you know from manufacturing overall, it's difficult to join different metals together, and one of the potentially useful applications of LOM of metals is for embedding different materials in aerospace structures and also embedding electronic or sensing features with good bonding to the substrate. So I think each of these processes, and we've talked about 7 different methods, will have its own niche as the additive manufacturing industry grows. I don't think any of the processes will necessarily go away, but we'll see the processes become more specialized and develop their own markets. And this list of 7 processes is actually the official categorization of the ASTM, the governing body that came up with the definition of additive manufacturing we stated earlier. I've ranked the processes from low energy to high energy, the lowest energy being stereolithography, which ASTM officially calls vat photopolymerization, and the highest energy being directed energy deposition or powder bed fusion. These are the processes that at present are used to print metals, and because you need to melt metals to 3D print them, you need to apply a lot of energy in the process. The 3 processes I've highlighted, photopolymerization, i.e. stereolithography, material extrusion, i.e. FDM, and powder bed fusion, i.e. SLM, are the 3 ones we'll discuss in more detail because at present I believe they're the most important and significant processes, and understanding them will let us get a general appreciation for the process physics involved in printing polymers, metals, and ceramics. And as we go forward, we also must appreciate that the printing process itself is only one step in the overall additive manufacturing sequence. In order to become masters, we need to know how to go from our 3D geometry to our finished part, which involves knowing the capabilities and limitations geometrically and how we designed for 3D printing, and the processes after printing, post-processing, removing support material, and finishing. And in certain cases, those additional steps after printing can be a significant fraction of the cost of additively manufacturing a part and could in some cases be more than the cost of 3D printing itself. So to close, we'll go back to our metal cubes we saw before, and here I have the MIT metal cube that we 3D printed, and I have the same geometry before it was cleaned up at the end of the 3D printing process. And if I find the same features on the right surface of the part, let me turn this around, you'll see, for example, the side view of the part after it's printed with support material needed to capture the overhanging features, and after the support was removed by mechanical means, digging it out and machining it away, and also after polishing. And even the attachment to the build plate is permanent, so the part has to be sliced off of the build plate by CNC milling or using a wire discharge machine. And this is a case where the post-processing is significant, and if you want to have a high-quality mirror finish, you have to do a lot of additional processing that contributes significantly to the cost of the process. Now let's talk in depth about extrusion additive manufacturing, which you may know as FFF, which stands for Fused Filament Fabrication, or FDM, which stands for Fused Deposition Modeling. In extrusion AM, we have a nozzle dispensing molten thermoplastic onto a build platform, and relative motion between the nozzle and the build platform, as we see in the video here, is how the part is built. You typically have 3 axes of motion, X, Y, and Z, all orthogonal, and by that coordination you can build curvilinear layers and complex geometries from the bottom up. Now, we're used to seeing most oftenly desktop FDM, and that's why FDM is the most widespread versatile additive manufacturing process. For a few hundred or a few $1,000s, you can buy a desktop FDM machine and do things like print objects such as an iPhone dock. However, the biggest part of the industry is actually industrial FDM, and Stratasys, the market leader, sells a line of machines they call the Fortis, and they cost typically over $100,000 and are used to print large, high-quality parts. One of their biggest applications is printing ductwork for aircraft, and customers such as Boeing and Airbus print hundreds of unique duct components for every jet they manufacture. And these big FDM machines might be found in those manufacturers' facilities or in service bureaus where you can order professionally FDM made parts. And this is a video of the FDM facility from Solid Concepts, a service bureau, and you can see the FDM machines in action. These are Stratasys Fortis machines. You get a sense of the real-time speed of the print head and how it needs to stop and start very quickly, in this case to make many of these vertically standing parts in parallel. As we zoom to a rendering of the process, this is the pre-processing, visualizing the tool path. And now this 3D model of the machine shows how the build material, the filament cartridges, are underneath the build platform. And up above in the heated chamber with the extrusion nozzles is where the part is built. The filament is fed up from the cartridges into the build chamber where the extrusion nozzles receive the filament, heat it, and extrude it onto the build platform. And if we look more closely, this machine has 2 extruders, one for build material and one for support material. And Stratasys machines typically have 2 materials, and the support is dissolvable, which lets you create a more complex, higher quality part without damaging the surface when you remove the support. Here we're seeing just schematically the print head laying out different materials, and this is printing a turbine wheel type part where the sparse white material is the support and the dense dark material is the part. Clearly you want enough support in the right place to support your part, but if you can print that at a sparse density, you can process the part faster. After the build is done, the technician removes the plate. In this case, they're using a transparent flexible plate to ease removal, and then there's mechanical and chemical removal of the support material. That can be a typically manually and painstaking process. And then here's using some wet chemistry and washing to finish the surface to give it its final texture and then smooth it to look like an injection molded part. Here are some storage containers of build material. Here are some different materials that they process. And then here's an example prototype game controller that has a rough texture on the back and a smooth texture on the surface. So one of the interesting and important attributes of FDM is you can buy a variety of thermoplastic materials. Stratasys machines are pretty closed. You typically have to buy their materials, but they've grown their market by offering more common thermoplastics such as ABS and nylon, all the way up to polycarbonate and ultim, high temperature thermoplastics. And those are the kinds of things used for those aircraft ducts because of high temperature requirements and also flammability and fume requirements. Here next to me printing, I have a desktop FDM machine. This is one we bought for about $500. It's made by a company in China. It's called the Up Mini, and you can see it moving as we speak. I'll lift the cover here, and you can see the print head moving from side to side. The filament cartridge is at the back. I have a cartridge over here, which is the same, with a spool of filament, typically about 2 millimeters in diameter. It's fed into the machine, into the print head, where you have a motor to drive the extruder, the heated nozzle, and a fan to keep the nozzle cool. And here, the print head is moving from left to right and we'll call this the X direction, and the build platform is moving from front to back in Y as well as in Z. And we're printing a small version of the MIT dome here. If we left this on, it might take about an hour or more to print. But to save time, just like we might be on a cooking show, we took a time-lapse video of the same process. Now at about 100 times accelerated, you see the process of the FDM machine building the part layer by layer. This is the base of the building, and in a second we'll see it transition to the dome where it changes its cross-section. And clearly the coordinated motion to achieve the curved cross-sections is important, to achieve an accurate smooth curve. And now it's done, and now I have the part over here under the camera. We can see the layerization of the part, the discretization of the toolpath, and if I turn it to the side, this model is a fairly simple geometry, fairly rectangular, and you see because this printer only prints a single material that has to be the support, the necessity to remove the support material leaves these residual defects. But by and large, a nice level of detail for printing a customized object quickly. Some more professional components, these were provided to us by Stratasys. These little sort of salt or pepper shaker models are meant to show the process of surface finishing, going from the initially printed part to a sanded part to a smoothed part where they actually use a chemical smoothing process. And you can't quite get the finish you get in a high quality injection molded part, but you can get pretty close. This part is an example of printing on a dissolvable support material. It's a pinwheel, kind of like we saw in the Solid Concepts video, but it's actually the first part I ever 3D printed when I took a prototyping class about 15 years ago when I was beginning graduate school. And I've saved this part to this day, and it's made out of FDM plastic, thermoplastic, and this is the dissolvable support material that Stratasys had just brought out at that time. And I mechanically removed this from the pinwheel, and then I put the pinwheel in a heated bath with the additive that helps the dissolution to clean it up. And you can see the discretization and layerization on the pinwheel part as well. Something more recent is this little ball bearing part with encapsulated spheres. And another thing you can do with FDM is print fully encapsulated assemblies. Though, for mechanical reasons, this might wear a lot more quickly than an engineered bearing, but can be good for prototyping a mechanism. And this little slingshot part, which is a single part as a mechanism, and if I release the lever here, it's going to spring up. So FDM, though simple, thermoplastic has quite a bit of versatility. The nomenclature of FDM parts are as follows. We typically refer the platform as the build plate, the material printed underneath the part as the support as well as the raft. The raft refers to the first few layers that are needed to assist separation of the part from the build platform, and then of course the part itself on top. This part is about 50 millimeters in diameter. It was printed on the Up Mini that we saw, and it was printed by a team of our students in the process of prototyping their yo-yo for the 2008 class. Now the parts you get out of a $500 FDM are not going to be as good in quality as a $100,000 FDM, but the parts will show the same intrinsic features resulting from the toolpath. And this is due to the discretization of the trajectory of extrusion and the fact that the nozzle has a fixed size and has to deposit material pretty much wherever it goes. So if you take a cross-section of any FDM feature that's fully solid, you'll find that it's made by a finish pass around the outside as well as an infill pass, which is cross-hatched to provide the requisite density of material. Here's a close-up picture of a cylindrical raised feature that I made. It's a couple millimeters wide, and you can see the deposition trajectory of the material both on the inside and on the outside. And imagine what happens as you want to make a feature smaller and smaller, but you can't change the diameter of material that you extrude. This comes into play if I want to, say, create these rectangular features with ever smaller gaps, then at some point the gap becomes wavy and vanishes because of the intrinsic precision. There are also trade-offs between, for example, accuracy and strength in toolpathing and part properties, and companies such as Stratasys that make professional FDMs have figured out how to best balance this trade-off. What I mean here is that if you want the highest accuracy, you have to keep the toolpaths just barely touching each other because you don't want the excess material to run into itself and cause deformation. But if you want highest strength, you need to have the best bonding between the consecutive depositions of material. So there are certainly trade-offs there. And the complexity of toolpathing and support design and adhesion between support and material layers, as evidenced by looking once again at our sample part made on the Up Mini. Here's the completed MIT dome in PLA, and here's the part that we stopped when we paused the printer during our break. And in this cross section you see here how it created the tool paths for the columns on the front, and also the fact that it has a fairly sparse lattice type infill. This is designed to speed up the printing process because this part doesn't need to carry a lot of load. And from the front we see the support structures that were deposited in front of the columns. My right thumb here is covered over the columns that we see on the left, and the extra material at the tops of the columns that was left when we mechanically removed the support. In FDM, we take a thermoplastic in solid form, heat it past its melt temperature, extrude it, and then allow it to solidify layer by layer to build our part. And there are some important similarities between that process and the process of injection molding, i.e. taking a solid feedstock, injecting it, and allowing it to solidify. However, of course, in FDM, you're cooling into open air, whereas in injection molding, you're cooling into a mold cavity. That said, we can take our basic understanding of polymer under heat and pressure, and we can apply that to FDM as well. We start out at room temperature with an amorphous thermoplastic. We heat it past its glass transition temperature where the chains loosen and can slip and align. And then we reach the melt temperature, and that's typically the set point temperature for the extruder, just like it's the set point temperature for our injection molding machine. And also in most FDM machines, the bed is heated to give good adhesion between the part and its flat support. However, we want to keep that temperature just below the glass transition temperature so the part doesn't peel away. Under the camera here I have a dual extruder, an extruder for a two-nozzle FDM machine where one nozzle would deposit support material and the other nozzle would deposit built material. And looking more closely, you see these are the two extrusion nozzles. This right side has had the fan cover removed, and we can see what we call the pinch wheel, which is how we grip the filament as it's forced down into the nozzle. This pinch wheel needs to provide enough force to counteract the viscous forces that are needed to heat the polymer and reduce it in its cross-section as it comes out of the nozzle. And the nozzle hole is probably too small to see, but it's here around all the solidified polymer. On the back side we have the motors that drive the extrusion pinch wheel mechanisms, just standard stepper motors, two of them side by side, and their rotary axis attaches to the gears that we saw that pinch the filament on the front face. Now I'm telling you about this because this is essentially the tool of the extrusion printer, but also its performance lets us understand what limits the rate and quality of the process. And for this we actually did an experiment. We took a similar extrusion print head from a desktop FDM, one with just one nozzle, and we instrumented it with a sensor to measure the force. So we could assess the relationship between the force required to force the filament through the nozzle, the feed rate, i.e. the velocity of the filament, and the temperature. And we gathered this data. And we saw, as you might expect, that the extrusion force increases with the required feed rate. The force is greater at lower temperature. If we have the print head set at a lower temperature, the viscosity of the plastic is higher, therefore we need more force. And also that there's a saturation to the force. The maximum force we could measure before the print head stopped working was about 60 newtons in this case. And then we looked more closely at what happened in the failure, and we found that the filament failed in shear. So that pointy wheel that we saw in the print head under the camera actually digs into the filament and creates indentations that allow it to apply the extrusive force. And at the point of 60 newtons, the material failed because the force required per unit area exceeded the shear strength of the material, and we simply could no longer grip the filament. So this is an example of how the FDM extrusion mechanism can fail mechanically. Now let's think about heat transfer and flow, and for this look more closely at the geometry of the nozzle. Above is the extrusion mechanism, and below is where the polymer is heated and reduced in cross-section, and we can decompose this nozzle geometrically into three sections. First is a wide section which roughly matches the diameter of the filament, about 2 millimeters. This is where the filament is heated primarily, and then there's a reduction in cross-section to the final nozzle diameter, and absent die swell, this matches the width of polymer that's extruded from the nozzle. So if we look at the coupling between heat and flow in this nozzle, we find that the rate at which FDM printing occurs is limited by heat transfer to the filament. These are some finite element simulations we did of the nozzle geometry. This is now true to scale, and we did these simulations at different feed rates of filament, 1 millimeter per second, 3 millimeters per second, and 9 millimeters per second. And from these renderings, we plotted the temperature along the center line of the extruder at these different feed rates. And we found that a feed rate of about 3 millimeters per second was the highest feed rate at which the temperature at the bottom of the large diameter section was equal to the melt temperature. And when you don't meet this heat transfer requirement, you require a much greater force to extrude the polymer because it's too cold and too viscous when it hits the nozzle, and therefore the printhead fails. These models and limits apply to small-scale FDM, as we defined it in terms of desktop machines or professional industrial machines such as those made by Stratasys. However, we're also seeing interesting innovations in large-scale extrusion additive manufacturing. You may have heard of the 3D printed car, or perhaps in the news last week, a 3D printed self-driving minibus made by Local Motors, a startup company in the US. And this is based on large-scale extrusion technology developed in part with Oak Ridge National Labs, a government and industry and academic collaboration in the US where they built this machine that they call BAM, Big Area Additive Manufacturing. It is a pellet-based polymer extruder on a large gantry, and it can achieve building of large-scale polymer parts by essentially FDM. And the sacrifice they're making here is one of resolution for increased rate. Instead of grams per hour, they can deposit in many kilograms per hour, but the resolution of their build, as you may measure by the layer thickness, is only a few millimeters relative to 100 microns that you'd find in a regular FDM machine. Also, because they're using pelletized plastic rather than filament, they can create custom composite blends, for example, taking thermoplastic ABS and adding chopped carbon fiber that gives the plastic its black color and also enhances the mechanical and thermal properties. I visited Oak Ridge National Lab a couple months ago and saw their largest BAM printer. This is literally the size of a house. I'm taking this from the second floor gantry, and this is many, many, many meters long, and you can see down here the periphery where they feed the pelletized plastic into the extruder. One of their applications is making tooling for composite manufacturing, particularly composite manufacturing of wind turbine blades that can be tens of meters long, and where if you can quickly make tooling that can be used to form the composite blades, you can quickly iterate on the blade geometry and perhaps customize to different regions where the wind turbine blades will be used. This is just one section, maybe 1 or 2 meters long, of a much longer multi-piece tool that would be made. They also had some vehicles like this. This is a Jeep-like vehicle, which was pretty impressive. And they say, well, this vehicle is made by 3D printing. Well, obviously, it's not all made by 3D printing. You know, you can see the tires and wheels and the mechanical components wouldn't be made by thermoplastic extrusion. But you do see, if you look a bit more closely, such as the backs of the seats, hey, we see the layerization that we know to be typical in FDM. And I was walking around on a tour, and I was asking, well, what about the hood? Is the hood made by 3D printing, or is it made out of metal? It kind of looks like it's made out of metal because it's smooth and shiny. And they said, oh no, this is also made by 3D printing, but they've developed coating and finishing processes that take the roughness off the layerized 3D printed parts and make them smooth. And this has been done in collaboration with polymer and materials companies that have helped them develop that additional technology that's necessary to turn the basic FDM parts into applications such as this. So in the future of extrusion, I see an interesting future from the small scale to the large scale, and I say that by comparing these two examples. First, I could, say, print a small chair, a model of a chair on my desktop FDM machine, like the little yellow chair I have in my hand. This takes about an hour to print, and if I want this for a model set that I'm building or as a prototype of my product to take to a meeting, an hour to make this is pretty satisfying. However, I can also use the BAM process to print a chair that I can sit in about 30 minutes. Oak Ridge National Lab printed this chair for me and sent it to my office where it's sitting, and you can see it's about the height of the doorknob. So clearly this is a much higher throughput process in terms of mass or volume per hour, but this is a much higher resolution process. By understanding the process parameters and limits to extrusion additive manufacturing, I think we're going to be able to develop more advanced technology that can span all these length scales for making things like personal models, customized objects, tooling, and even perhaps vehicle structures. Now, to really master FDM as a manufacturing process, we must learn about some other topics. First, we must understand the criteria for support structures. If you think of what is necessary to support a part as you build it, if you have a certain angle that becomes close to the horizontal, you're going to need to build secondary structure to support that overhanging feature. And the criteria for support depend on the geometry, the orientation of the part, the material, and even the machine. You also want to learn about the mechanical properties of parts that you build. One of the most important things about FDM extruded parts is that they're anisotropic. That means that the strength of a part will be different if you pull along the filament direction versus perpendicular to the filament direction. Results are getting better, processes are getting better, but typically parts are still a few tenths of % weaker in terms of their strength perpendicular versus parallel. and also ways to finish parts. We saw this in the video from Solid Concepts. There are established methods using mechanical or chemical means such as solvent vapors to go from the rough surface to the smooth surface, whether it's a small part or a large part such as the vehicle hood that I just described. We don't have time to get to these in detail, but you'd certainly see a lot of information about them if you search online or if you look up a more advanced additive manufacturing course. Additive manufacturing by photopolymerization is what we commonly call stereolithography, or SLA. And it involves scanning a laser across a bath of photocurable polymer, as we see here in a video from Materialize, one of the world's largest 3D printing service bureaus and design houses. The material is being recoated by this blade, and then the laser is scanning across the bath. After a really long time using this large machine, we see the finished part emerge from the bath, kind of like a sea monster emerging from the sea, because it has a complex geometry and lots of interesting curves and supports. Now, stereolithography is a single material process, and as we zoom into the part, you'll see the support structures, the scaffolding, and the part itself. And when we see the operators taking the part out of the machine, you'll notice that the process of support material is often manual and laborious because you have to separate mechanically the support structure from the part itself. And optimizing the topology of the support, the orientation of the part, and having an easy removal of the support is an important process consideration. Materialize has several of these machines, and they use them to make, for example, automotive prototype components, bumpers and interior components, taking advantage of the large scale of the machine and the high detail of the process, which is limited by the spot size of the laser. So here's a diagram of stereolithography. Imagine this diagram applying to the large vat that we just saw, and what we don't see above the machine is the laser optics and scanning system that scans the laser beam very accurately and quickly over the bath. This is a regular orientation SLA machine where the part is incremented down into the bath upon each layer. So when the laser is done scanning each layer, the part increments down, and then the recoater comes across and spreads a smooth layer of resin, which defines the thickness of the subsequently cured layer. There are many applications of SLA that profit from the high level of detail, which is the differentiating factor versus FDM. For example, prototype parts like this case that might be for a piece of consumer electronics, short-run tooling for doing small cycles of injection molding or thermal forming, presentation models, high-detail parts for visualization within meetings or engaging customers, architects to automotive companies, for example, as well as a few personalized products. I previously mentioned Invisalign, which makes the transparent alternative to orthodontic braces, and they use stereolithography as the molds for customized thermal forming of their eventual product. Also, most hearing aids are made by stereolithography today. And just like we did with FDM, here's a time-lapse video of that part being made. We'll see the build platform move up in Z, and also the build platform oscillate a little bit, and this oscillatory motion is needed to detach the part from the window that the laser shines through as I described. You can see the display of the machine increments the layer number, and once the build is complete, the platform will rise all the way out of the resin bath, and then you can open the cover and take out the part and do the post-processing. What we were making is a small chess rook, and here is the part as it would appear coming out of the printer. Once it's pried off the build plate, it would look like this, and we see a couple interesting and important things. First, that there's this large support structure needed to support the part and keep it attached to the build platform. Second, the software for the Form 1 says that the best orientation for the build is not straight up and down, but is at this angle, and this is needed to minimize the surface area of attachment between the part and the support. And this is the part after the support has been removed, and because one side is unsupported and the other side is supported, you see that you have remnants of the support where it was detached, and more post-processing, more polishing could be done to clean it up, but this is part of the painstaking process of post-processing. Here's a couple parts we made in class. Again, for our yo-yo project, a team recently made a hamster yo-yo. The idea was to have a little plastic hamster that ran around the inside of the yo-yo as the yo-yo spun. And in the prototyping process, we made small hamsters by stereolithography to demonstrate what the hamster would look like. And here again is tipped in the inverted configuration as the part would be built, what the support structure would look like and what the part would look like, and then you have to remove the part from the support in order to use it. Comparing SLA to FDM, we notice that typically the layer thicknesses of SLA can be smaller than FDM. So here I've taken two identical parts, the little salt pepper shaker parts, one made on the Stratasys Mojo, a desktop FDM that has model and support material, dissolvable support, and the Form 1 SLA. And this is a side view of the SLA part, and this is a side view of the FDM part. And here we've configured the Form 1 to have a layer thickness of 25 microns, which is about 1/4 of the layer thickness of the FDM. So certainly if you have a thinner layer, you need to print more layers. So the SLA process is slower if you have thinner layers, but you can get higher detail and better surface quality in SLA than you can in FDM. And if we look at the top around one of the holes of the salt shaker, we see a different tool path, but the same idea, that the scanning of the tool, whether it be the scanning laser beam rastering across each layer or the scanning extrusion head dispensing across each layer, has some of the same characteristics, i.e. an infill trajectory and a perimeter trajectory needed to give a smooth, fine edge as best as possible. So now let's talk a bit about the fundamentals of photopolymerization, i.e. if I pulled the Form 1 back in and looked closely, you would see that there's light flashing. You can see light flashing at the interface between the build plate and the resin. That flash of light is what's causing the resin to polymerize, to go from a viscous liquid to a solid that creates our final part. This photoresin is a complex mixture, and it involves what's called a photoinitiator, a special molecule that initiates photopolymerization of the polymer that ends up being your part. So when this photoinitiator receives a photon of the appropriate light wavelength, for which the laser is chosen in the machine, the photoinitiator becomes reactive and then reacts with the polymer molecules that are in the photoresin, forms polymer chains, and those form together to form a three-dimensional polymer network, a cross-link network that's analogous to a thermoset. And this can be rigid or soft depending on the chemistry of the photopolymer you choose, and you can write the general chemical equations for it involving the action of light on the photoinitiator to form a radical, and then the interaction with the radical photoinitiator and monomers to form polymer chains, and then the continued polymerization of polymer chains to form the network. And when the chains run into each other, they terminate and the process is complete. You can find a great chapter in the additive manufacturing textbook by Gibson, Rosen, and Stucker that goes through the fundamentals of photopolymerization in detail. Here I highlight a few things that let us understand at a high level what limits the rate and resolution of the process. First, consider when the laser beam is scanning across the surface of the resin, we have a distribution of intensity. We often say that the laser beam has a certain diameter, but actually it has a distribution of intensity across this diameter. This means that if you measured the number of photons hitting the surface of the resin, they would be maximum in the center of the spot and decaying as you go farther outside. If you convolve this intensity distribution on the surface with the fact that the resin absorbs light, you can derive that each laser pass cures a parabolic cross-section of the resin. What I mean here is if you imagine you're sitting on the surface of the resin, say going for a swim if you will, and you measured the intensity of light and measured the amount of polymer that was photocured, you would find that you form a parabolic noodle of cured resin each time the laser passes. Now you can relate this cure depth, i.e. the depth of the parabola, to parameters of the photoresin that can be measured and calibrated. In fact, you can derive a log linear relationship between the cure depth of the resin and the exposure, or the amount of energy in millijoules per unit area. And when you surpass a certain critical minimum intensity to cure the resin, you have this log linear relationship. And it's the slope and the intercept of this line that let you take the reported parameters of a photoresin and match them with the performance characteristics of a particular stereolithography system. If we look at the cross-section of a stereolithography part, here it's a little example of a plastic turbine blade that I printed, we can see the fact that the laser is not printing isolated parabolas, but rather parabolas that overlap. Just as we'll see next in selective laser melting, to build a contiguous full-density part, you need to have good adhesion between the rods laterally and the layers vertically. And also something that's important and a bit behind the scenes is that polymers shrink as they cure, and stress is developed as you go from the fluid molecules with a higher free volume than their polymerized counterparts. So the intelligence inside stereolithography machines under development for a long time actually executes a zigzag scan pattern that's designed to give a uniform contiguous solid part, but to try to reduce the amount of shrinkage and stress that you get. And the chemistry of the resin is also important to that. So if I look at this cross-section, we can see roughly each horizontal line represents a layer, and each vertical column represents the laser spot size. And you can see that the laser is going back and forth with every consecutive laser. And you're actually curing into the previous layer a little bit more to make sure the next layer is well adhered to the part itself. Here are the specifications of the Form 1 desktop SLA printer. The build volume is about 100 to 150 millimeters on a side in a rough cube form. And the minimum feature size is determined by the spot size of the laser. Here it's 300 microns, or 0.3 millimeters. While the layer thickness is determined by the thickness of resin that's recoated and the underlying mechanism for that. Here it can go as small as 25 microns, and I believe be set at 25, 50, or 100 microns. So this difference between the minimum feature size and the layer thickness is one you'll see in most SLA systems. I want to look a bit closer inside the Form 1, and particularly at the mechanism that's used to scan the laser. Now remember, the part is built inverted, vertically, pulled out of the resin bath. So here's the build platform, and here's a rendering of the part. If we open up the bottom of the machine where we had that digital display, you would find that there's a few mirrors in the laser source. And it's the scanning of those mirrors that positions the laser at any two-dimensional point at the interface where the photopolymerization occurs. And so this sequence of arrows is meant to show how the light comes out of the laser and reflects off two rotary scanning mirrors, scanned used what are called galvanometers, and then a fixed mirror that goes upward into the bath. And from the Form 1 that we disassembled, I have the scanning apparatus here. This is why I'm wearing the nice blue gloves. Here is the laser unit. One of the innovations of Formlabs in bringing low-cost SLA to market is they used low-cost blue lasers used in DVD players. And if I flip it over, we see the laser source coming in, hits off these two mirrors that are attached to the galvanometers, the rotating sources. Those are really impressive electromechanical devices that you can read about, and you can imagine the laser bouncing off one galvanometer, the other galvanometer, whose angles will vary rapidly according to the toolpath, and then bouncing off this final fixed mirror and going up into the build area. So this is the orientation as in the machine. From a machine design perspective, or from the perspective of manufacturing SLA machines, you also have to very accurately position the galvanometers and the mirrors inside this frame. And that's why we have a high precision CNC machined frame with compliant mechanisms to appropriately grip and constrain the laser and the two galvanometers. So companies such as Formlabs also have to learn about manufacturing their 3D printers and manufacturing them for consistent performance, as well as understanding the 3D printing manufacturing process itself. To conclude, here's a set of specifications from a large-scale industrial SLA machine, this one made by 3D Systems. And in the Formlabs machine, we had a laser that's about 100 milliwatts. In this case, we have a laser that's 1,450 milliwatts. And in fact, this machine has two different lasers, or one laser that gets split into two different spots, a large spot that it can use to build the interior of the part, which it calls the large hatch spot, and a smaller spot, which it calls the border spot, which can use to do fine detail on the support part attachment points as well as the outside edge. So here in this industrial machine, you're able to use a different, more complex design to perhaps improve the throughput and improve the quality of parts that can be made. So having learned about additive manufacturing of polymers, let's now talk about additive manufacturing of metals. And here our topic is powder bed fusion, but you must know these processes more commonly as selective laser sintering, SLS, or selective laser melting, SLM. Here's a video of the selective laser melting process in action. It's from EOS, a German company that is the world leader in selective laser melting machines. And here you see an operator mounting an insert to a base plate and loading it into a metal 3D printer, an SLM machine. After he clamps the build plate into the chamber, he closes the chamber, and the machine checks the position of the base plate, and then starts the process. You'll see the laser scanning across the powder surface. The emission of light and sparks indicates the significant amount of heat involved, and this is printing a part out of steel. This rendering shows the process step by step, sequential spreading of powder and scanning of the laser. The real process doesn't speed up like shown here, but it of course requires many layers to build the finished part, and this likely takes many hours. When the process is done, we've built up this cone-shaped part, which is a tooling insert to be used in injection molding, as we'll see later. And there's a lot of unmelted powder, which is recycled if possible after the process is done. The process requires a lot of careful cleaning, and it's not as nice and neat as shown here, but you can see nicely the finished part that the operator is removing once cooled and then taking off the build plate, which can be reused. Now after the print, post-processing is required, in this case hardening at high temperature up to a certain Rockwell level, and then the part goes to another company, a partner of EOS, where CNC machining is done. CNC machining of the surface is needed to give the characteristics for this use in injection molding, and then even manual polishing to give the mirror finish. And after the insert is all ready, it goes to the injection molder. It's used in a standard injection molding machine here, and there you see it. And it's used to mold disposable plastic drinking cups. And the advantage we haven't seen yet is that this part, because of additive manufacturing, has conformal cooling passages that can reduce the cycle time and also enable better thermal uniformity for higher part quality. And the statement here is that the productivity of the process is improved by 70%. That's a really big deal, and it can of course justify the increased cost and complexity of additive manufacturing, especially because additive manufacturing of metals, SLM, is really expensive and painstaking these days. So here's a diagram of the process we just saw. In this case showing schematically the manufacturing of a chess piece. You have the machine sequentially spreading powder layer by layer, the laser scanning the corresponding cross-section of the part, and then the build plate incrementing down and the machine spreading powder again. Very careful, complicated process, but simple in its mechanism, whereby you build the part layer by layer as in the other processes we've discussed. Now SLM is finding wide application. Metal 3D printing is really hot these days. The aerospace industry is thinking about 3D printing jet engine parts out of metal to produce advanced material components, things like turbine blades and fuel nozzles, for example, GE's new fuel nozzle, and space companies such as SpaceX are using 3D printing quite a lot. Also, Airbus and others have advanced more simple things like aircraft brackets. This is a bracket for a cargo door where it's beneficial if you can use 3D printing to reduce its weight while maintaining its strength needed for its use. The example we just saw, conformal cooling channels within injection mold tools, and then as we'll discuss later, medical applications, medical implants where the complex geometries, advanced materials, and ability to improve performance within the body is a compelling factor to use SLM manufacturing. But also powder fusion, as I gave the general title, applies to many materials. Polymers, of course metals, ferrous metals and non-ferrous metals, and even ceramics and composites. And while these are less widespread applications, you might be thinking that the process of scanning a laser over a powder can pretty much apply to anything, as long as you get the physics and process parameters right. And that's correct, and you could look more deeply into these topics. And with respect to selective laser melting, or more properly selective laser sintering of polymers, many consumer products companies, in this case Dyson, use polymer SLS for prototyping, and they make full assemblies of their vacuum cleaners for testing in their laboratories and testing with customers. Again, a great example of additive manufacturing used to accelerate the product development process. Here's an SLM machine that I saw in a laboratory. About a year ago, I visited Nanyang Technological University, NTU, in Singapore, and they have a beautiful lab with lots of industrial professional 3D printers. Here's one from SLM Solutions, another German company, and you see the laser unit over here, separated from the main printer. This is where the part is printed, equivalent to the window we were looking through in the video, and then the powder control and electronics are all in the rest of the unit. Now, inside the box, we have the optics and mechanics that control the laser and the spreading of powder. The laser source is, of course, separate in a cabinet but connected by a fiber, and then above the print bed you have a series of optics, typically scanning optics, galvanometers, same thing we saw in stereolithography, and then a lens that makes sure the laser is maintained in the right position. That's called an F-theta lens. And then the mechanism of holding the part and spreading the powder. This needs to be quite parallel and accurate because you're talking powder layers that need to be uniform over hundreds of millimeters, but be 100 microns or less in thickness, and also maintain that precision with temperature. And then the part can get quite heavy, so the mechanism has to be able to make small increments while holding a heavy part. The process of SLM is very complicated. It may seem simple, but there are many critical process parameters: the laser power, the scan speed, the scan pattern, the size and packing density of the particles, the uniformity and thickness of the layers, the temperature of the bed and the build area, as well as the atmosphere, and many more. And the process is so complicated that We must at present rely more so on empirical understanding guided by the physics of melt pool formation to optimize the process to deal with particular materials. And a critical component of the SLM machine is, of course, the laser being over here connected to the printer by a fiber. And I just want to say that you, of course, want to choose the laser and its wavelength and its energy so you can couple strongly to your material. So metals have decaying optical absorption with increasing wavelength. This is about 1 micron above the visible to 10 microns the far infrared. And metals absorb well in the low infrared, so you typically choose a 1 micron to 2 micron wavelength laser for a metal 3D printer. If you have a polymer laser printer, you're typically choosing a wavelength farther out of about 10 microns, because that's where polymers have the highest absorbance. So what's different between SLM and FDM and SLA? Well, first, because we use a powder as the feedstock, we can choose from many different materials. This powder is typically 10 to 100 microns in diameter, the individual powder grain, with a wide size distribution, and that influences our resolution and layer thickness. Now, second, a downside of handling powder is that it's complex and dangerous. Powders can be flammable. You typically don't want to inhale them. And also they can oxidize easily, and that's why machines such as that EOS metal printer have to have an inert atmosphere to prevent powder oxidation. The energy required is high. We talked about SLA having fairly low power lasers to execute the photoreaction. That might be a watt or a few watts or even a tenth of a watt. At the other end, SLM machines typically have 10 to 100 or even 1,000 watt lasers that are needed to provide the high energy necessary to melt the powder. And last, post-processing for SLM is complex. Not only is it hard to remove the powder and clean the part, and you have to pay attention to all the complex issues above, but also, for example, in metal parts, you need to machine away the supports and machine the part off the build plate. That adds a lot of extra time and cost. Let's look more closely at the mechanism of SLM. Here you have the laser beam moving from right to left, and as it moves, it melts the powder. Ahead of the laser is the unmelted powder, and behind the laser is the solidified metal. You want to go from loosely packed powder that you can spread to a fully dense solid metal. And in between, under the laser, and a bit ahead and a bit behind, is what we call the melt pool. This is where all the action happens. And you can also see that the laser melts and the melt pool extends down into the previous layer, because like in SLA, we want to melt or cure down below the fresh powder so we have a monolithic full density part. Here's what it looks like before and after. This is, for example, what you'd see if you zoomed in on the powder bed before the laser came by. The polydisperse powders, this is a titanium aluminum vanadium powder typically used in SLM, and after the laser comes back and forth in a zigzag fashion, you see the evidence of continuous melt tracks, which is likely a good quality part. Now, to choose the layer thickness, you might choose the powder size, i.e. you want the powder size to be smaller than your layer thickness. And you can buy powders over a wide range of sizes, from very small, in this case 25 micron average diameter smaller, all the way up to 100 microns or greater. And by looking at these pictures, you can imagine the handling considerations and the handling mechanics can also be different. And that comes into the design of the recoating mechanism within the SLM machine. I have a few parts here under the camera just to show you this little frame, which is made out of an aluminum alloy on an SLM machine. You can see the evidence of the diagonal melt tracks going back and forth to zigzag across the part. This part is very light and small, but probably takes tens of minutes to manufacture. And then I have these little cubes, kind of like six-sided dice with MIT on the side. And recall, this one has not been post-processed, and you see how it's been cut off the build plate and there's support in this internal feature. And this has had the support removed, the base plate removed, and also it's been polished. We also see on the top surface of the unfinished part the evidence of the laser scan pattern. It's a bit harder to see than on the frame we just saw, but you see there are different checkerboard regions here. And this is because the scan pattern is globally divided into many regions, and that's needed to guarantee uniformity of heat flow and reduce the residual stress as the part cools. Those are both very important and complex issues. In the basic mechanism of SLM, we want the laser to scan across the powder, form a melt pool, and then leave a continuous solid track of material behind. One way to optimize the process is to develop a process map considering variables of laser power on the vertical axis here and scan speed on the horizontal axis here. This is a figure from a recent study from the University of Louisville where they developed a process map for Ti64, the titanium aluminum vanadium alloy that's very common in SLM. They identify 4 regions wherein energy density increases from the bottom right to the top left. Region 1 is their best identified region where they observe the part to be fully dense with few defects, and that's what you see from the top view, the evidence of the continuous melt tracks. In the other regions, for example Zone 2, which has a higher energy density, the top surface looks good, but they find subsurface voids, basically open cavities underneath the surface of the part, and that's because of the excess heating that nucleates metal vapor bubbles. Those are really bad defects for mechanical properties. In Zone 3, the one with the lowest energy density, there's underheating. It means there's not enough energy density to fully melt the powder. The top surface is rough, and it's so rough that you can cause problems for the machine in that the recoater blade can jam when it's applying the next layer of powder. And in the fourth region, the overheated region, you have excessive evaporation and heating on the surface, and that also leads to a rough condition. So this is one way you might tune in the process for a new material or a new powder if you're operating your SLM machine. But of course, the physics are much more complicated than this. And Professor Jean-Pierre Cruth, who's one of the long-standing SLM experts, he's from Belgium and has written many excellent review papers and also developed many SLM technologies in the marketplace, says the following. During SLM, the short interaction of the powder bed and the heat source caused by the high scanning speed of the laser beam leads to rapid heating, melting, followed by drastic shrinkage and circulation of the molten metal driven by surface tension gradients coupled with temperature gradients. Now imagine the laser scanning at about 1 meter per second and that melt region being a fraction of a millimeter, maybe 100 microns or less. And a material such as steel might need to go up 1,000 degrees and down 1,000 degrees to melt and solidify. So we're talking about temperature gradients of up to 1,000,000 degrees per second or more. And he goes on to say that the resulting heat transfer and fluid flow affect the size and shape of the melt pool, the cooling rate, and the transformation reactions in the melt pool in the heat-affected zone. And the melt pool geometry in turn influences the grain growth and resulting microstructure of the part. Now this is quite a mouthful, and it's really telling us that everything is coupled. If you want to optimize and tailor the microstructure of a part, great opportunities for metal additive manufacturing, you need to understand all these complex physics. Also, you need to understand enough about the coupling of the laser and the material and the powder and the heat flow and the fluid flow to give good quality parts everywhere in a complex build. And we're now just developing the computational capabilities for this. I took this video attending a presentation at an additive manufacturing conference last year by Dr. Wayne King, who heads the simulation group in additive manufacturing at Livermore Laboratory in the United States. And this is a slowed down supercomputer simulation of the formation of the melt pool by the laser running over the powder bed. And you can see that it looks essentially like a boat going through water. The melt flow is extremely dynamic, and you may also see little pieces of material being ejected off into space. Those are the sparks that we see in a video of the SLM process. It's material ejection caused by the extremely rapid vapor flows and capillary pressures that exist at the surface. And because the molten metal is penetrating into unmelted powder and solidifying rapidly, you have significant roughness, and not only in the top surface but also on the edge. And further understanding these fundamental factors are going to be important to optimize SLM in the future. And if we step forward several years, we might be able to apply computational tools like this into the real design process. Back to more practical aspects, typically the scan pattern for an SLM machine is checkerboarded, as we saw on the small frame part or on the cube part, and the island size and relative directions of the scan are tailored to give a good uniform local heating without having excessive temperature gradients over the part entirely. And the machine software will have developed scan algorithms and perhaps optimize the scan pattern depending on the size and geometry of the part you want to make. Now, what does success look like? Well, success of a high productivity build might be something like this. A couple years ago, Renishaw, which makes SLM machines like EOS, put out the example that they had built a titanium bike frame using SLM. Well, they made individual parts of the bike frame using SLM, and then they put the bike frame together. Together, the frame weighed only 1,400 grams, 1.4 kilograms, so extremely lightweight. And the successful build process is exemplified by many parts in close proximity, where you can also see the support structures. Clearly this part has been cleaned up. We don't have the residual powder after the build process, but to run SLM in a high productivity situation, you're going to have to establish a capability like this. Now, at the opposite end, when things don't work right, your parts might crack and deform. And we don't have much time to get into it, but suffice to say that residual stress that's trapped in the part upon cooling, because the whole thing gets locally hot and locally cool, but also is warm as the process proceeds, are really important issues to optimize and understand. So this example from Professor Tim Simpson at Penn State, which is a big metal 3D printing center, shows in printing these large monolithic parts the fact that the residual stress was strong enough to crack the part upon cooling, to deform it, to break it, and to pull it away from the build plate. And this is an extreme case, but even small deformations can be deleterious to accuracy or mechanical properties. And the ability to maintain integrity of the part and also understand how to heat treat it appropriately to relieve these stresses is essential to getting metal 3D printed parts into real demanding applications. Mechanical properties of SLM parts are themselves an involved topic, and often you need heat treatment after the print process to give the right microstructure and the right mechanics, i.e. to relieve that residual stress. And the state of the art now for well-known SLM materials is that if you understand all those aspects, you can create a part with strength and stiffness that's comparable, or in some cases even better than conventionally processed alloys of the same composition. Better can be because of the fine grain structure that you get because of the rapid local heating and cooling. But the one thing that SLM parts are generally not as good at is in strain to failure and fatigue properties, because the strain to failure and fatigue properties are really sensitive to small defects, and we just don't understand enough about the SLM process to control it to eliminate all small defects that influence those properties. Now, SLS and SLM machines have been available for several years, but only recently are we seeing it becoming arguably the fastest growing segment of the industry. And that's because there's significant market pull for metal 3D printed parts, as well as growth in the machine technology. In 2015, almost 1,000 metal printers were sold around the world every year, and that's about a 50% increase over the previous year. People in the industry say that it took 20 years to sell the first 1,000 machines, and now that we're selling 1,000 machines or more a year. And the annual sales of products fabricated by metal 3D printers is almost $100 million. Now, 1,000 isn't that many machines relative to how many milling machines are sold, and one reason, of course, is that the metal 3D printers, the SLMs, are expensive. It might cost you no less than $500,000, but up to several $1 million to buy an SLM machine, and that depends on the size, the build volume, the laser power, the number of lasers, and the integration of the machine with other processes, like extra build boxes and heat up versus cool down chambers to amplify productivity. In the coming years, we're going to see the cost of machines drop, of course, as volume and demand goes up, and we might see some alternative, more desktop or shop-friendly metal 3D printers come onto the market. And existing players, as well as startups, such as Desktop Metal, are working on those technologies. And to grow the metal 3D printing industry as fast as possible, we not only need better machines, but we need pull from application. So one of the fastest growing applications is, of course, medical implants. And here I show you a bit more about the hip implant cups, the acetabular cups that are made by e-beam melting or selective laser melting. The cup is the cup that is part of the hip implant overall and is mounted into the pelvic bone of the patient, providing the socket of the ball and socket joint. And last time I checked, there were over 40,000 of these cups implanted in patients in Europe and US, where they're both approved by the FDA-like agencies. And the reason why this is a compelling application is not that it's customized, maybe it would be in the future, but that metal 3D printing lets us create a very special surface texture, essentially a surface lattice, that improves the rate and strength of integration with the bone. And of course, after the patient receives the hip implant, you want he or she to heal as quickly as possible and not experience failure of the joint. And that is why additive manufacturing is a compelling solution, because you can't create this easily with conventional processes. I have a couple parts here under the camera. Now these are made by Arcam, which makes e-beam melting machines. We didn't talk about electron beam melting, but just think of replacing the laser with an electron beam and it melts the metal in a similar way. I've been told these are made in stacks, so they're stacked vertically in the machine, maybe 8, one after the other, and each one takes about 30 minutes of build time. Here I have a part that has a lot of excess powder in it. Some of the excess powder has come off as it was removed from the machine, but this contrasts the quality of the part and what it looks like after the printing versus half of it after the post-machining is done. You can see a lot of cleanup, blasting away the powder, as well as CNC machining and polishing is needed to give it the final quality. And if we zoom in at the lattice structure, we can just try to capture the surface texture in cross-section that gives it its special properties. And in the future, we're certain to see many tailored applications like this and large market applications that allow us to invest the time and research into understanding the processability of specialized materials by SLM. The field of additive manufacturing is advancing very rapidly, and by the time you watch this video, there'll probably be several even more exciting innovations. However, I thought I'd conclude by highlighting some emerging process technologies that I think will be important and are very interesting. First is high-speed polymer 3D printing. One example of that is the technology of Carbon 3D, a startup based in California that has taken the conventional stereolithography process, the inverted stereolithography process, and added one important inventive step. Between the light source, which is underneath the resin path, and the part being built, they have an oxygen-permeable window. And by supplying oxygen through this window, they can inhibit polymerization. So the equations we saw before for photopolymerization can be modulated in their rate and their kinetics by the presence of oxygen. What this means is they can continuously print. They don't have to layerize. They can use a projector underneath the build window, and they can project a full cross-section of the part at a time. And this part that we just saw in the time-lapse video itself was printed in 7 minutes, whereas it might take 70 minutes or more to print it on a machine such as the Form 1. This faster rate printing is very attractive for industry and for prototyping, even though the machine might be more complex or costly. Also, because they can project these images continuously, they can make parts with very smooth surfaces, essentially playing a movie on the projector. And they're still at the early stages, but they've released that they have many customers in industry, such as Ford printing parts for automotive prototyping and perhaps small volume production, as well as customers in Hollywood printing parts for capturing Hollywood special effects scenes in movies. Another important axis is the industrialization of additive manufacturing. Here I mean automation of the process. In the case of selective laser melting, which is complex and involves many hazards such as high-power lasers and removal and handling of powder, it's attractive to think of what it would take to create a production line that can automate all of those steps. So a startup based in the Netherlands called Additive Industries has put together expertise in machine design and software and optics to build a single production line that can produce parts by SLM in sequence. And this allows the user to load build platforms that are heated, printed upon, and then the parts are removed from the build plate automatically and stored in a queue. And this kind of machine can run for several days and exercise many times the build volume of the printer itself continuously. They've just installed their first system at Airbus, one of their partner customers, and they have a nice video on YouTube showing the installation of the machine. A third area of innovation is hybrid additive manufacturing. Here by hybrid I mean combination of additive deposition and subtractive removal of material. One company doing this is DMG Mori, who I may have spoken of in the machining lecture. They're one of the world's leading precision machine tool companies, and here they have a direct-write metal 3D printer that sprays powder through a nozzle with a laser so you can build up parts layer by layer, as you can see here, the heat and the growth of the part. And then after you're done printing the part or printing a piece of your final component, you can take the laser head and load it in a tool changer and then take a milling head. It's basically a combination of a direct-write metal 3D printer with a 5-axis CNC milling machine that can execute both processes in one setup. This is advantageous because you can achieve high-quality net-shaped parts without having to dismount and remount the part. You can also take advantage of the precision of CNC machining and the fact that if you can remove material with the CNC, you can deposit a bit faster using the 3D printing process. They're showing here the manufacturing of a complex part, something with vanes, with complex 3D geometries like you might use in an aircraft engine. And while this machine is expensive, I've heard $1 or $2 million, and must be synchronized between both operations, those parts are high value for applications such as aircraft. Here's another part that they showed, a different kind of turbine housing that has these plugs radially coming out from the side of it, and this part is made in about 7 hours. This process is still at an early stage of development. All the issues of residual stress and cooling and material oxidation and contamination are at play, but for certain applications I'm sure in the future we'll see machine tools in machine shops that can do both additive and subtractive and take advantage of those attributes. I got to visit DMG Mori's research facility in Tokyo a while ago, and the lead scientist who developed the machine gave me a personal demo of it. It was really impressive to see up front. It's also a huge machine, fills a typical office or more, and has many different modules, including for the laser and the tool changer and the cooling units. But I saw it build parts from the bottom up and then machine the surface, and this is the piece of the turbine blade that was made first, and it built this by the 3D printing step in a period of about 20 20 minutes and then had to wait for about 5 minutes so the part would cool just enough so it could do the machining operation. And last, we're seeing incredible innovations in materials. One example is Mark Forged, yet another startup. There's a lot of great startup activity that's very creative. And they are taking conventional FDM in a way and adapting it to fiber composites. They actually have a patented process where they combine a thermoplastic filament with a continuous strand of advanced fiber, such as carbon fiber or Kevlar or nylon, and there you can print fiber-reinforced parts, useful for applications such as tooling and fixtures or bicycle components. And they report they can make parts that are of the same specific strength as aluminum, which is really exciting. And then more exotic things. We may not know yet the exact full spectrum of applications of things like integrating 3D printing with electronics. And the company Voxelate has developed a process to print conductive inks, basically wiring within thermoplastic FDM. And one example of their process is this 3D printed quad rotor. Basically the structure is 3D printed and the circuitry is laid inside. And this is an X-ray radiograph, and the wires that connect the circuitry and control system in the center to the motors that are at the corners are printed monolithically within the structure. So the flexibility to design things like consumer electronics might be enhanced if instead of assembling the wiring into the housing, we can think of printing the wiring monolithically with the housing. Now we've come to the conclusion of our discussion of additive manufacturing, and principally we've focused on three major processes. First, extrusion additive manufacturing, or fused deposition modeling, FDM. Second, photopolymerization, commonly called stereolithography or SLA. And third, powder fusion, where we referred to selective laser melting or SLM for metal additive manufacturing. Looking at our four favorite process attributes, cost, rate, quality, and flexibility, we can understand that for large-scale manufacturing, all additive manufacturing techniques can't compete with the conventional processes in terms of cost and rate and quality. However, for producing parts quickly or on demand, it's attractive to think of additive as a prototyping or an increasingly attractive low-volume production process. Of course, for flexibility, the opportunities are immense in terms of creating new materials, complex geometries, and in the guise of short, quick production, reducing the design cycle by prototyping or making tooling using additive technologies. Now, also we can appreciate that the answer to these attributes for a particular additive technology is not a simple and single point one. For example, extrusion we saw can happen at the small scale or the large scale, from desktop FDM to the big area additive manufacturing process that you can use to print a large piece of tooling for turbine blade manufacturing or a piece of a vehicle. And there we have trade-offs between rate and quality, and also trade-offs between rate and quality and cost. And we can think of the excessive value that can be brought by the 3D printing process. Maybe itself it's expensive, more expensive than the alternative, but it can bring value to the component or value to accelerating a development or a testing cycle. Now there are many challenges that we must face and overcome to accelerate the adoption of additive. And these include first, design tools and data management tools to fully realize the potential of additive, to assist engineers in designing parts so they can take advantage of the flexibility of additive but not run into bounds in feature size or orientation, for example. And the more parts that we 3D print and the more parts that we can scan into the cloud, we can learn from the parts that have been made and make our processes better. Also improved process control, and I mean this from the end of simulation to actually controlling the machines to qualifying the parts by taking data real-time while printing is happening. And this will let us create parts with higher quality at faster rate and qualify components so we know that they don't have deleterious defects, for example, hidden beneath the surface when they're made. And with any manufacturing industry, standards will be important, so actors all along the supply chain can speak the same language. So materials can be quantified in terms of their attributes and their properties, and parts can be qualified for service. And also education, from academia to industry, accelerating our understanding of additive from fundamentals to applications is a challenge for us as educators and us as students. And actually the number one thing that I hear from companies, from industry, when I speak to them across industry is the need for improved education. So they can educate their engineers and designers as well as educate their customers on the importance of additive manufacturing. And last, I really feel that additive manufacturing will be a catalyst to supply chains of the future. I don't necessarily think that we'll have 3D printers in all of our homes or that additive manufacturing, at least for a very, very long time, will replace a significant fraction of global manufacturing. However, the advantages of additive in terms of its flexibility and on-demand availability means that it can shift the balance between local and global production. And also we can think of additive manufacturing as one component in the future digital infrastructure of manufacturing that involves not only 3D printing, but improved robotics and automation and accelerated software and ability to gather and exchange data. And on this note, there's an excellent report by IBM called The New Software-Defined Supply Chain, and it talks about all these trends coming together, where 3D printing is only one piece of a much larger puzzle that'll influence manufacturing in the future.